Hello friends, in this lecture we will study directional relay. Before studying the principle of directional relay, let us consider the radial distribution system with single source that we have studied in overcurrent relay. So in this radial system there are three relays connected, R1, R2 and this is R3, and these bus will provide power supply to the load. So in case of overcurrent relay, we have studied that let's say if there is a fault at this point, so for this fault the fault current will flow like this, okay, and R2 will provide the primary protection, and if R2 fails to provide the protection, in that case R1 will provide the remote backup protection. Similarly, if fault occurs between these two buses, let's say this is bus A, B, C, D. So if there is a fault in the feeder between bus C and D, so for this kind of fault R3 will provide primary protection which will be fast, and if R3 fails to provide the protection, R2 will provide remote backup protection. So this much we have studied in overcurrent relay. Now again consider the same system, the same radial distribution system, but a source is connected to another end. So this is the radial distribution system with two sources. Let's say this is source 2. Now again consider a fault between B and C. Now for this kind of fault, the fault current will flow from both the ends. A fault current will flow from source 1 and another fault current will flow from source 2. Okay. Now if there is a fault at this point, ideally what should happen? Since fault is between B and C, so the part of circuit or the part of power system between B and C should be isolated. In preferable condition, the part of feeder that is between B and C should be isolated. This part should be isolated, and whatever load is connected at bus C, this should continue to get the power supply. But what will happen here? For this direction of current, let's say this will provide the primary protection, okay, so this part of circuit will be removed. For this direction of fault current, we have fault at this point. For this direction of fault current, R3 will be, the relay R3 will operate, and after operation of this relay, the bus or the load which is connected to bus C, the power supply to this load bus will be interrupted, which is not a preferable case. Okay, so this is a problem if we provide protection from one end only. This protection was for source 1 only. Let us connect the relay again. So what can be the possible solution? If fault is at this point, this relay should operate, and for this type of fault current, instead of relay R3, there should be relay at this point which should be operated. Let's say if we have a relay here, R1, R2, this is R3, let's say this is R2 dash. So for this fault, instead of relay R3, if relay R2 is operated, so this part will be open circuited, and whatever load is connected to bus C will continue to get the power supply. So this will be the preferable case. So let us connect a relay here, R2 dash. So now it seems that our problem has been solved. But again a problem here is, if there is a fault at this point, the same fault current will flow through R3 and R2 dash. For this kind of fault, we will say that same fault current will flow through R2 dash and R3. So both of these relay will compete for their operation. If R2 dash relay operate prior to R3, then it's okay, but there is an equal chance that relay R3 will operate prior to R2 dash. So in that case again we will have the same problem of the disconnection of load at the bus C. Okay, so our problem has still not been solved. Our problem here is that both the relays R2 dash and R3 are connected to same bus, so the same fault current will flow through both the relays. So there is an equal chance that both the relay can operate, any one of these relay can operate prior to the other. Now again one possible solution may be, for this fault the possible solution may be set the TMS of R3 greater than TMS of R2. If TMS of R3 is greater than TMS of R2 for the same fault current or the same value of, we'll say that for the same value of PSM, operating time of T operating time of R3 will be greater than T operating time of R2. This we have studied in previous lecture. Okay, so if we will set TMS of R3 greater than TMS of R2, now what will happen? The same fault current will flow like in both the relays, but now the operating time of R2 dash is less than operating time of relay R3. So this relay will trip before R3. So now our problem is solved. Now it seems that our problem has been solved. But again consider a fault at this point. Now for this fault, what should be the preferable condition for this kind of fault? This part of the power system should be isolated. Okay, for this direction of fault current, let's say this relay will operate and this part will be disconnected, so it's okay. Now for the fault current which will be flowing from source 1, again we have the same full fault current will be flowing through R2 dash and R3. Now since the time multiplier setting of R2 is less than R3, so this relay will operate prior to R3. So here this part of circuit will be disconnected, which is not the preferable case. Preferably R3 relay should have been operated, but R2 dash has operated because it is faster than the relay R3. So again we have the same kind of problem if we change the location of fault. Okay, so in a radial distribution system having two sources, we should have relay at both the ends of feeder. Okay, this relay will provide protection for the fault current which will be flowing from source 1, and corresponding to source 2 we should have relay at the other end of the feeders. But still we are left with the problem how to discriminate or how to differentiate between the two relays which are connected at the same bus, like this relay and this relay. For the fault at this point, we want this relay to operate, but there is an equal chance that this relay may come into the operation. Similarly, on the other side, these two relays are connected to same bus. For this fault, we want this relay to operate first, but there is an equal chance that this relay may operate prior to the prior to this relay. This is R1, R2, R3. Let's say this is R2 and this is R2 dash. This is R3 and this is R3 dash. And let's say this point A. For fault at A, preferably R2 dash and R3 should be operated. But there is an equal chance that R2 will operate prior to R2 dash and R3 dash will operate prior to R3 because these two relays have equal fault current. Now here we will realize the need of directional current. Okay, for this fault, the direction of current in R2 will be from left to right. So let us assume that R2 dash should operate when the direction of current is from left to right, and for fault A, if R3 should be operated, the direction of current in R3 is from right to left. So let us assume that for these two direction of current, these two relay will operate. And for the same fault, we don't want the relay R2 to operate. But for this fault, the direction of fault current in R2 will be left to right. So we don't want this relay to operate. So let us say for this direction of current, relay R2 will not operate. Similarly, for this direction of current, R3 relay will not operate. So we have total four conditions on relay R2, R2 dash, R3 and R3 dash. For this direction of current, R2 dash and R3 should operate, and for the same direction of current, R2 and R3 dash should not operate. Okay. Now consider the fault at this point. For fault at this point, preferably R1 and R2 should operate. Okay. And what will be the direction of current in R1? The direction of current will be left to right. So let's say for left to right, this relay will operate. And for this fault, what will be direction of current in R2? The direction of current in R2 will be from right to left. The condition on R2 is, according to this fault, the condition in R2 is it should not be operated for left to right direction of current, but it will operate from right to left direction of current. So R2 relay will operate. So for this fault, R1 and R2 will operate. So the problem of fault at this point is solved. Now again consider the problem of fault between bus 3 and bus 4. For this fault, the relay R4 should operate for this direction of current, and the direction of fault current in R3 will be from left to right. The relay, according to this fault, relay R3 should not be operated for a direction of current from right to left, but for this fault demands relay R3 to operate for the direction of current from left to right. So this will operate here. So we have considered different fault at the different possible points. Okay, and in each relay I have added a constraint that each relay will operate for a single direction of current only, and using that condition the problem of fault at each possible point is solved. Okay, so if we make a relay to operate only for one direction of current, okay, that relay will be called directional relay. Okay, and let's say a relay, if this relay operates for left to right direction of current, for this relay we will indicate an arrow from left to right. Similarly, if a relay operates for right to left direction of current, accordingly we will indicate an arrow. You may also observe that since relay R1 is at bus 1, okay, although I have shown a gap here, but relay R1, you have to consider that this relay is just after the bus 1. You never have to consider a fault at this point. Okay, the direction of fault current in relay R1 will always be from left to right. Okay, so this relay need not be the directional relay. The direction of current in this relay may be left to right and right to left, so this has to be directional, this has to be directional, and these two relay also need to be directional. Again, consider the relay R4, the direction of current is only from right to left, so this need not be directional. So these relays are essentially overcurrent relays with directional constraints. If an overcurrent relay, these are overcurrent relay with directional constraint. Okay, this will be called directional overcurrent relay. The relay should not be operated only on the basis of direction of current. The amount of current should also be large enough. So that decision will be taken by overcurrent relay, and the decision about the direction will be taken by directional relay. So the total operation will be done by both directional and overcurrent relay. So if we will add the directional constraint in an overcurrent relay, that relay will be directional overcurrent relay. Now let us study principle of directional relay. Consider a part of power system, and this is a relay which is connected to, let's say this is bus A, this relay is connected to bus B, this is bus C. Okay, this is potential or voltage transformer. So with this transformer, this bus voltage, this, although just for drawing the diagram I have separated this point from B, there is a separation between the point B, but essentially this potential transformer will give information about bus voltage B to the relay. Okay, so this is nothing but bus B voltage. Okay, so this way the current, fault current, and the voltage will be fed to the relay. Now let us consider a point P, fault at point P. So for fault at point P, the direction of current in the main line will be from right to left. Okay, there will be a voltage. In case of fault, the voltage of a bus decreases sharply, so there will be some voltage here. Okay, and the direction of current will be from right to left. So for this direction of current, accordingly a current will be induced in the current transformer. Since in the main line current is leaving from the dot, so using transformer action a current will enter into the dot. So let's say this is the direction of current, and since there is a fault here, this part will be short circuited, and the feeder or the line is mostly reactive, so the current will approximately lag this voltage by 90 degree. So if I make the voltage as reference, the current will lag, this current will lag the voltage by 90 degree. This is the fault current corresponding to fault at point P1. Now in the second case, consider a fault between bus B and C at point P2. So for this fault, again we will have a potential drop across the winding of potential transformer, but now the current direction of fault current will be reversed in the main line, and if this direction will be reversed, current in the secondary of current transformer, this will also get reversed. So the reference of voltage will be same, but now the new fault current is in opposite direction to the previous fault current. So the phasor of new fault current will be this should be in opposite direction to the previous fault current. Let us name this current as IP2. Okay, so if the previous current was lagging by 90 degree, if the previous fault current was lagging the voltage by 90 degree, the new fault current will be leading the reference voltage by 90 degree. And this is the principle used in directional relay. For one direction of current, for fault in one direction, the current is lagging, and for the other direction of fault current, the current becomes leading. For this phasor diagram, I have assumed that the feeder is purely reactive, but in practical case, the feeder will have some resistance, so the current will not lag exactly by 90 degree. This will be the fault current, and let's say this angle is phi. Okay, so anyway, this direction of fault current is lagging. So if a current is lagging, it will be treated as the fault at point P, or it will be treated as one directional. Okay, so this is the region of lagging current. Okay, in this region, the current is lagging the reference voltage, and this is the region of leading current. So lagging current means this direction of current, and suppose you want this relay to operate for this direction of current. Conversely, you can say that you want this relay to operate for lagging current. So this is the region of lagging current. So in this region, the relay should trip, or the relay should be permitted to trip. And in this region, the relay operation will be blocked. If we will consider a lagging angle other than 90 degree, so we will draw approximately a perpendicular here. This will give you a region of lagging current. So this will be in this region, trip decision will be issued, and in this region, in this region, the relay operation will be blocked. As I said earlier, a directional relay can only detect the direction of current, it cannot detect a fault. Okay, so there should be an additional relay to detect the fault, like a directional overcurrent relay. There will be a directional relay to detect the direction of current, and overcurrent relay will make the decision about whether a fault has occurred in the line or not. So let us understand the operation of directional overcurrent relay. this is directional relay and this is overcurrent relay. This is directional overcurrent relay. Let's say this relay is made to operate for this direction of current. So for this direction of current, the directional relay will trip or this will close the circuit. Since the overcurrent relay is connected in series with the directional relay, so overcurrent relay can operate only when if this circuit is closed or the directional relay trips. Okay, so let's say for this direction of current, the directional relay closes its connection or it trips. So the circuit is completed. Now if this in this direction the current is, let's say this is fault current, so according to the magnitude of the current, this can be detected as a fault current or normal current by this overcurrent relay. But if the current is flowing in opposite direction, using the phase principle, this direction of current, for this direction of current, the directional relay will open its connection or it will block the operation of relay. Since this is connected in series with the overcurrent relay, now it does not matter what is the magnitude of current in this direction. Since this circuit has been opened, so overcurrent relay cannot detect this current as a fault current. Okay, after studying overcurrent relay and directional relay, now we will study distance protection or impedance relay. So for studying principle of this kind of relay, let us consider a simple system of source, two buses. These two are connected through the transmission line. Okay, now let us consider the impedance seen by the source. If no load is connected or the load end is left open circuited, so obviously there will be no flow of current. There will not be any flow of current. So the impedance seen by the source, this will be V divided by 0, this will be infinite. If a load is connected here, so the total impedance seen by the source will be the impedance of load and the impedance of transmission line. In that case, load seen at source will be load impedance plus impedance of transmission line. Okay, now suppose a fault occurs in the middle of transmission line. So this part will be short circuited. Now in this condition, what will be impedance seen by source? Now the impedance seen by source will be the impedance that is contributed by this part of line only. Okay, since impedance is symmetrically distributed in the transmission line, so whatever impedance is contributed by this part of line will be directly proportional to the length of this line. So let's say this length is m fraction of the total length of transmission line. So this impedance will be m into z line. And since this is short circuited, so the load impedance will not be seen by the source. So the impedance seen by the source in case of fault will be m into z line, and obviously m will be less than 1. It does not matter where in the line fault occurs. Let's say fault occurs at this point. In this case also, what will be the impedance seen by source? Impedance seen by source will always be less than z line. Okay. So if impedance seen by source is more than z line, we can say that the total impedance will be load impedance plus z line. So in this case there is no fault. But if a fault occurs, obviously the impedance seen by the source will be less than the total impedance of line. In that case we can say that a fault has occurred in between the line. And this is the principle of distance protection or impedance relay. And the impedance seen by source, this is represented as apparent impedance. In this case, in case of fault, the ratio of apparent impedance to the z line, this will be less than 1. and this impedance is measured by with the measurement of voltage and current. We take these are phasor quantities. Okay, so if these are phasor quantities, Z apparent will be complex, and if Z apparent is complex, we can say that distance protection is inherently directional. One more thing here we can observe that if fault occurs right in the middle of transmission line, what will be the measured or the apparent impedance? The apparent impedance will be half of the transmission line impedance, or conversely we can say that if the apparent impedance is half of the total line impedance, it indicates that fault has occurred in the middle of the line. So with this protection, the position of the fault can be located. Fault can be located. If only magnitude of the apparent impedance is used, okay, we will say that if this magnitude is less than the magnitude of line impedance, it will detect the fault. So based on this, if only magnitude is used, this relay will not be directional, and this will be called impedance relay. So if Z apparent is less than the Z line, so the mod of Z line will represent a circle with radius equal to mod of Z line, and if apparent impedance is less than, that is within this circle, so this region will be trip region. This is trip region and this is block region, and this will be non-directional. This will be real part of Z, this is imaginary part of Z. If we add directional constraint, so how is the VI characteristic of a directional relay? This was V, this was I, this was trip region, this was the phase difference angle phi. So if we want to convert this diagram into impedance diagram, in the impedance diagram, here we will have imaginary part of Z, real part of Z, and the angle of Z will be the lag angle. So this will be phi. Draw perpendicular to it. This will give you trip region, and this is block region. So this is impedance characteristic of a directional relay. So if we will add directional constraint to the impedance relay, just draw a line here and remove this part. This is characteristic of impedance relay with directional constraint. This is characteristic of impedance relay. This is ZR is the reference impedance. If impedance seen by the source is less than ZR, the relay will operate. This is trip region. Okay. So this is non-directional impedance relay. This is impedance relay with directional constraint. A modified impedance relay is obtained if we offset the center of impedance circle from origin. If we shift the center of this impedance circle from origin, we will get modified impedance relay. And this is also called mode relay. This length is ZR. The radius of circle of modified impedance relay is half of the radius of circle of the corresponding impedance relay. And since this relay operates only for first quadrant of impedance circle, this relay is directional. This is directional and has better selectivity for high power factor load. As I discussed earlier, the principle of the operation of impedance relay is we measure the apparent impedance seen by source, and if this impedance is less than the total line impedance, we can say that a fault has occurred. Okay. Or instead of this line impedance, it is not necessary that apparent impedance is always compared with the total line impedance. Instead of this line impedance, Z apparent is compared with the reference impedance, and this reference impedance can be chosen independently. This reference impedance may be less than the total line impedance. Okay, let's say if ZR is 0.8 of line impedance, it means if the apparent impedance is less than 0.8 of line impedance, we will say that fault has occurred. So the reference impedance can be chosen independently. Let's say this length represents the 80% of the line. So up to here we will have this total impedance. This will be 0.8 of ZL. Okay. Now if a fault occurs at this point, and let's say up to here, this length represents the 90% of the length. So up to here the total impedance will be, or up to this point the apparent impedance will be 0.9 into ZL. And let's say for impedance relay here, let's say reference is set as 0.8 ZL. Okay. Now for the detection of fault, what I said, a fault has occurred at the 90% of the length of line. So the apparent impedance seen by source will be 0.9 into the total impedance of the line. And let's say the reference impedance is set at 0.8 ZL, that is 80% of the total impedance of the line. Now for the detection of fault, apparent impedance and reference impedance is compared. If apparent impedance is less than reference impedance, we will say fault has occurred, or we will say fault will be detected. Fault is detected or relay will operate. Now whether this condition is satisfied here, Z, the apparent impedance is greater than reference impedance, so fault will not be detected, although fault has occurred, but fault is not detected. So at this point fault has not been detected. What about this point? Let's say this represents the 60% of the line. So up to this point the impedance seen by source will be 0.6 into ZL. and reference is 0.8 into ZL. Okay, apparent impedance is 60% of ZL and reference is 80% of ZL. So for this fault will be detected. So we can say that if any fault occurs between source and 80% of the line, between source and 80% length of the line, this fault will be detected, and any fault that occurs beyond the 80% of line, for this kind of fault, the apparent impedance seen by source will be greater than the reference impedance. So these faults will not be detected. So here we will define the reach of the line. Reach of the impedance relay. It represents distance down the line up to which fault will be detected. Suppose for this line, if ZR is set at 0.8 ZL, so reach of the line will be, here reach of the impedance relay will be 80% only. Up to 80% from the source, if a fault occurs, that fault will be detected. Beyond 80% length of the line, fault cannot be detected. Using impedance relay having reference impedance is equal to 0.8 ZL. In a power system, a relay is provided with multiple zones of protection. To understand it, let us consider a power system. In this power system, we have buses A, B, C, D and E, and we have relays R1 to R8. Since I have indicated a direction, it means these relays are directional relay. And since we are studying distance protection, so these are directional impedance relay. And directional impedance relay is nothing but mode relay. Okay. We have already discussed what is the meaning of this direction. It means for this direction of fault current, this relay will be operated. For opposite direction of fault current, although this is a fault current, this fault current this relay will not operate. Okay, so as I have said that in a power system, a relay will be provided with multiple zones of protection. Okay. Relay is provided with multiple zones of protection. For example, relay 1 will be provided with, for relay 1, there will be 3 zones of protection. Zone 1 protection, zone 2, and 3 types of protection will be inbuilt within a relay. Okay, so zone 1 protection is provided for the protection of this primary line. Okay, like for relay 1, the zone 1 protection will be primarily for this line. Okay, and reach of zone 1 protection is 80%. It means if a fault will occur from the relay, if a fault will occur up to 80% distance on the line, this fault will be detected by zone 1 protection. Okay, and zone 1 protection is, this is fast and without any intentional delay. If a fault occurs beyond 80% of line, let's say a fault occurs at 90% of the line, this fault will not be detected by zone 1 protection of the relay 1. Okay, so but it does not mean there is no provision for detection of this fault. This fault will be detected by zone 2 protection. Now one can ask a question that why this part of primary line has been left? Why not to set zone 1 protection for 100% reach? Let's say zone 1 protection, zone 1 is for 100% reach. Now what will happen? Or before discussing this, let us observe that the relay R2, R3, R5 and R7 are connected to same bus P. Although I have drawn it at different places, but in power system these 4 relays will be connected at a same place only, or these are connected to bus B only. Okay, for any fault between bus B and C, R3 will provide primary protection. Similarly, for any fault, let's say if any fault occurs here, let's say this is fault 1, this is fault 2, this is fault 3 and this is fault 4. So for fault 3, R3 will provide primary protection, and if it fails to protect, okay, if this relay fails to operate, this relay will not provide a backup protection because this is directional. Okay, if a fault occurs here, the current will flow like this. So for this direction of current, this relay will not operate. So for this fault, if primary protection fails to operate, the remote backup protection will be provided by relay R1. Similarly, for this fault, the primary protection is by R5 and the remote protection is by R1. So R1 is providing remote protection for fault F2, F3 and F4, and it is providing the primary protection for fault F1. Now let's say the zone 1 protection of relay 1, the reach of zone 1 protection of relay 1 is 100%. That is, the zone 1 is providing protection up to full length of the line. That is, if Z apparent is greater than, if Z apparent is less than the total impedance of line, this fault will be detected by zone 1 of relay 1. Now let us consider a fault occurs near bus P, just right side to the bus P. Okay, if a fault occurs at this point, so what will be the total impedance, or can you have the estimation of the total impedance? If we will measure from relay R1, so from relay R1, this will give you the 100% impedance of this line, this primary line, and since fault has occurred at near bus B only, here you will have a very small impedance. So for a fault near bus B, total apparent impedance seen by relay R1, this will be 100% of, this will be approximately equal to 100% of line 1, 100% of primary line. And for the fault detection, if Z apparent R1 is less than the Z reference of R1 or Z reference of zone 1 protection of R1, which is 100%, that is Z line. So we will say that Z apparent as measured by relay 1, if this is less than Z line, we will say that relay 1 will operate. Okay, so this is the condition. This is the condition for zone 1 protection of relay 1, for the operation of zone 1 protection of relay 1. Okay, now again come back to this fault. For this fault, it seems that the total impedance seen by relay will be greater than Z line, because if you will start from here, the total impedance of Z line will be included, and there will be some impedance depending upon how far the fault has occurred from bus P. Okay, so theoretically it seems that the apparent impedance as seen by R1, this will be greater than line 1. Okay, and if it is greater than line 1, the zone 1 protection, zone 1 of relay 1 will not be operated. But only the theoretical value will be greater than the Z line. In case of relay, this will be measured by V divided by I. Z apparent as seen by relay 1 will be operated. This will be calculated by the reading of potential transformer and the reading of current transformer, and both potential transformer and current transformer, they are not free from errors. There will have some error in the reading of potential and current transformer. Also, the current transformer is not free from saturation. When theoretically we are considering, we are estimating the total impedance seen by relay R1, we are not considering any fault impedance here. Okay, so we are taking many approximations or many ideal situations which may not occur practically. So if we consider, so considering all these non-ideality which we are taking as ideal, the actual Z apparent as seen by R1 may be calculated as, or may be read as, less than the line impedance. Okay, this actual may be line impedance, because this will be calculated by the reading of potential and current transformer. So now what will happen? If this condition is satisfied, for this fault, relay R1 and relay R3 will compete for their operation. Okay, if relay R3 is operated first, then it is okay, but if relay R1 is operated first, for this fault, unnecessarily this part of circuit or this part of our system will be isolated. Okay, fault is here, but because of this fault, if relay R1 is operated, if this is operated, the whole power system will be disconnected from bus A, which is not the desired, which is not the favorable condition. But if we set the reach of zone 1 protection to 80% only, let's say this is 80% only, so ZR will be 0.8 ZL only. Okay, now for a fault F3, the impedance seen by relay R1 will be Z apparent relay R1, which should be theoretically, this must be greater than Z line theoretically. Okay, but we'll say, let me write down in detail. for a fault at F3, the apparent impedance seen by relay R1, Z apparent as seen by relay R1, this must be greater than Z line. Let's say this is, because fault is at here, so this whole impedance will be included. Let's say this is line 1, this line 1. This must be greater than Z line theoretically, but Z apparent R1 as measured by relay may be slightly less than, let's say 0.95 Z line. Okay, although theoretically Z apparent as seen by relay 1 must be greater than Z line 1, but since this is measured by relay and that measurement is not free from error, that measurement is not ideal, so that even for this fault the Z apparent as measured by relay 1 may be slightly less than the total total impedance of the line 1. So in this case, and what is reason for this? Because measurement has been done practically, because measurement has been done by many components like current transformer, potential transformer, which are not free from non-ideality. So in that case, what will happen? Z apparent as measured by R1, which is equal to 0.95 Z line, let's say it is 0.95 Z line, and this will be less than the reference impedance if reference impedance is set at 100% of the Z line. In this case, what will happen? In this case, for fault at F3, relay R1 and relay R3 will compete for their operation, which is not desirable. So to avoid this condition, what should be done? To avoid this condition, let us put a lower value of reference impedance. So if we will put ZR is equal to 80% of the Z line, let's say 0.8 Z line, and error in the measurement or the non-ideality is not as high that the apparent impedance measured by R1 will be less than 0.8 of the Z line. What I say, theoretically up to this point the impedance should be greater than Z line, but non-ideality is not as high that this impedance will be less than 0.8 of Z line. Okay, so choosing Z reference for zone 1 protection as 0.88 Z line is safe considering the non-idealities. So if this is chosen, this condition will never satisfied. If this condition will never be satisfied for this fault, this relay and this relay will not compete for each other. Okay, for this fault, the condition for operation of this relay will not be satisfied. So first this relay will be operated. Okay, so this is the reason for setting reach of zone 1 protection of relay 1 up to 80% only. Now coming to the zone 2 protection of relay 1. The zone 2 protection will start after a coordination time interval only. Okay. This will be started after 0.3 second only, as there will be 3 zone of protection for R1. Similarly, for all other relays there will be 3 zones of protection. Say for R3, zone 1 protection will be extremely fast. This will be without any intentional delay. Okay, and zone 2 protection will be after an intentional delay that is measured by coordination time interval, and it is 0.3 second. Now again consider this fault F3. In case R3 fails to protect, if R3 fails to protect, if a fault is near bus P, and if R3 fails to protect, there should be a backup protection. So the backup protection will be provided by relay 1, and backup protection should always be after a coordination time interval. So zone 2 is already operated after a coordination time interval. So the zone 2 protection of relay 1 will be used for providing backup for R3 as well as for R5 and R7. So we will say that zone 2 protection of relay R1 will be used for backup protection for R3/R5/R7 if fault is near bus only. What I am saying is R1 will provide backup protection for R3, R5 and R7 for those faults only which are near bus P. Okay, let's say if a fault occurs near bus C at this point. Okay, so for this point R1 is not, the zone 2 protection of R1 is not going to provide backup protection. The zone 2 of R1 will provide backup protection only for those faults which are near bus B. Okay. Also, the zone 1 protection is only up to 80% of the line 1. So rest 20% of line 1 will be provided by, this will be protected by zone 2 protection of relay 1. 20% of primary line will be protected zone 2 protection, and this is not true only for relay 1. For relay R3 also zone 1 protection will be provided up to 80% of primary line only, and rest 20% of the line will be protected by zone 2 protection of R3. Okay. Now the question is, what should be the reach of zone 2 protection? Reach of zone 2 protection. Okay, so zone 2 protection has to cover, it has to cover all this complete length of primary line. So it must be at least 100%, it must be at least 100% of primary line. So ZR, I am first choosing ZR as ZL. Now let's say a fault has occurred near bus P at this point. So again, Z apparent will be measured by apparatus. Okay, and there will be, theoretically, if you are at bus B, Z apparent should be Z line theoretically, but practically Z apparent, due to errors, let us consider 5% error or 10% error. Okay, so this will be from 0.9 ZL to 1.1 ZL, that is 90% ZL to Z apparent may be 110% of ZL. Okay, so now let us consider for a fault at this point, Z apparent as measured by apparatus is slightly greater than ZL. Let's say this is 110%, that is 1.1 ZL, and let's say the reach of zone 2 protection is ZR is ZL only, ZR is equal to ZL only. So in this case, the apparent impedance is outside the reference. ZR is chosen at ZL only, and the apparent impedance for this point, due to error, measurement of apparent impedance is 1.1 ZL. It is here. So this fault will not be detected. Okay. Now, when this fault will be detected? If this point will lie under the Z reference circle. So for that, we need to increase the value of Z reference. So Z reference should be increased. So for a safe value, the safe reach of zone 2 protection is 120% of primary line. So for a fault at this point, even you will have error in the measurement. Okay, the error has some prescribed limit, let's say 10%. So for this point, the maximum measured apparent impedance will be 110% or 1.1 ZL. ZR is equal to 1.2 ZL. So ZR is greater than the measured impedance, so this fault will be detected. So this was about the rest of the line, and not only this line, the relay R1 also has to provide the backup protection for R3, R5 and R7 if a fault occurs near bus P. So let's say a fault occurs at this point. Okay, this point means I have to show this point right to this relay. That's why a distance of this much appears to us, but this point is at B only. So the theoretical value of the total impedance should be approximately equal to ZL, but again there may be some variation. So for providing backup protection, Again, apparent impedance may be slightly greater than length of the line. So for this apparent impedance also, if we put the reference value 120% of ZL, so for this kind of fault also, zone 2 of relay 1 will provide backup protection. And same will happen for fault 2. Let's say a fault 2 is nearby bus, and similarly for fault 4. Now coming to zone 3 protection of relay 1. This will be operated after 2 coordination time interval, that is 0.6 second. As we discussed in the case of zone 2 protection, that zone 2 protection of relay 1 does not provide backup protection for the whole remote line. Okay, this provide backup protection for only those faults which are on the remote line but near bus B. Okay, so the purpose of zone 3, this is to provide backup protection for all remote lines. Okay, or we can also say that the purpose of zone 3 protection of relay 1 is to provide backup protection for the longest remote line. Let's say this is the longest remote line. So if it is providing backup protection for the longest remote line, obviously this will also provide backup protection for other lines which are smaller than the longest one. So we will say that to provide backup protection for the longest remote line. Okay, so what should be the reach of zone 3 protection? Since it has to provide protection for the longest line, and reach will be measured from relay 1 only, so it has to cover all the complete length of primary line plus complete length of the longest line, and plus for error you will have to take 10% margin. As we took 20% margin in the previous case, in this case also we will have to take 10% margin. Okay, so the reference impedance for zone 3 protection should be Z line 1 plus 110% of impedance of longest line. If we draw the impedance diagram of relay, where we will have imaginary part of Z, real part of Z. Let's say this point represent impedance of line 1. Okay, this will be boundary of zone 1, and this length represent the impedance of this point is at B. So this length represent impedance as seen by relay, impedance up to bus B as seen by relay R1. And for zone 1 protection, the reach of the line is 80% only, So this length I have drawn only 80% of the length, let's say OP. The reach of zone 2 is 120% of this total impedance. This total impedance is represented by point B. So we have to draw a point which is at 120% of OP. So let's say this length is 120% of OP. So this is the reach of Z2. This point is B. This is Z2. And Z3 is, this whole impedance is OP. Let's say this impedance is OD. So the total impedance will be OB plus impedance of the longest line. So let's say D is here, and Z3 will be OB plus 110% of OD. This point is D, and this is boundary of Z3. Now let us draw the time diagram of the 3 zone of protection. This represent distance from distance from relay R1. For zone 1 protection should be extremely fast without any delay. So we will keep T zone 1 as small as possible. This is T zone 1, and reach is up to 80% of the primary line. After zone 1 protection, there will be a time interval of 0.3 second, and from here zone 2 protection will start. So reach of zone 2 protection is 120% of primary line. So let's say here is the 120% of line 1. And after this point, zone 3 protection will start. So again we will have a jump of 0.3 second, and this will go up to 110% of this longest line. This is T zone 2, this is T zone 3.